I haven't seen a dentist in months now. This is really getting ridiculous. I'm sure we're all tiring of COVID, but we've got lots more work to do. Today's lesson is 5.3, and today we're working on banked curves in the unit of circular motion. Okay, so today's lesson is on banked curves. So as we're going around corners, properly engineered roads are banked in such a way that we can get away with a lot less friction and still corner safely. The biggest change with these questions from ones that we were working on before is that the normal force in this case is the hypotenuse of the triangle. This is going to be the largest force involved. Gravity is going to be equal and opposite to a piece of the normal force. We have a situation where things are unbalanced. And what I mean by that is we actually have to have some leftover force. There has to be some force that doesn't cancel out. A piece of the normal force is directed inwards, and that is what allows us to go around the corner. So that net force is our centripetal force, which causes our mass to undergo a centripetal acceleration and continue around a circle. So again, the biggest change is the force of gravity is not going to be the hypotenuse of the triangle. This will be equal and opposite to the upwards component of the normal force. As before, you need to read through all of the notes, and I'm going to pause, flip over the page, and go through some given examples, and then I'm going to go through some examples that you'll need to be able to replicate. Okay, so I'm going to start with an explanation of what here is called case 2. This is the simplest case. In this case, we're going to be moving at the ideal speed. I'll sometimes call it the perfect speed. In this case, there won't be any friction necessary. We will be traveling at exactly the speed that doesn't have any friction directed up the slope or any friction directed down the slope. In this case, we're going to see that the centripetal force is a moderate amount. It's the in-between value. So in this case, no friction means we only have two real forces. Of course, gravity is always there, and we have our normal force directed 90 degrees from the surface, and this is the largest force. This is the hypotenuse of the triangle, and Fg is going to be equal and opposite to the upwards component of the normal force. And that's where we have balance, because we're neither sinking into the surface nor are we accelerating up into the air as if we were a helium balloon. So our unbalanced force, our net force, is going to be the horizontal component of the normal force, and that will be our centripetal force. Now, case 1 and case 3, as you can see, are really quite complicated. When you're doing questions like this in practice, you're going to really want a large diagram, really large. This is barely appropriate because we really need to have enough space to show all the forces in there. So if we're moving too fast, what's going to happen is the car is going to want to climb up the grade to create a larger radius so that it can still make the corner. Now in this case, because the car is trying to track upwards, the force of friction is in the opposite direction to intended motion. So if the surface is made of a suitably rough material, if our tires are grippy enough, we'll also have friction directed this way. Now friction is made of two components. There is the horizontal component, which will contribute to our centripetal force. There's also a downwards vertical component that together with gravity will be equal and opposite to the upwards component of the normal force. So in this case, we're going to have one real force down, a second piece of a real force down, and those are going to balance added together. Those will be worth the same as the upwards piece of the normal force. In this case, the normal force will be quite large, and as well, we're going to have a very large centripetal force. Now in case 3, we're going far too slow. So in case 3, we're going so slow that the vehicle is going to want to slide down the surface. In a case like this, if the surface is made of a suitably rough material like asphalt and our car has good tires, then the force of friction will be directed up the slope. So in this case, gravity is the one and only force going down, whereas the upwards component of friction and the upwards component of the normal force added together are the two forces directed up, and those two added together will be equal and opposite to the force of gravity. In a case like this, Fn is quite reduced, and when we're looking at the centripetal force, that's the sum of the two horizontal forces, but the normal horizontal force directed in and the force of friction is directed out. So in this case, it's going to be winning force minus losing force gives us a very, very small centripetal force. And this makes sense because we're going extremely slow. So if we're going really, really, really slow, you don't need a very large force to keep you moving in that circle. Now, don't panic. You're going to practice all three of these cases, but when it comes to testing, you're not going to have to do complete questions start to finish on any case other than case 2. In case 1 and case 3, you might be asked to look at a diagram or draw a diagram, but you won't have to go through a very, very, very long derivations to get these done in a test situation. Now, this first sample problem is significantly more complicated than the typical question you'd have to do because we're actually creating a formula. So it certainly is far higher up the skill level to be able to create a formula than it is to just put values into it. So I'm going to go slow. I'm going to go through and make sure that the ability to get angles in works out for you. So I'd like to start with the diagram. Now, I extended this line here and showed that there's a right angle there. So I then have angle phi that we are banked at, and I'm just going to put a little dot there. And so this triangle shows that phi plus this angle here with a dot is worth 90. So phi plus dot is worth 90. But I see here from my diagram here that by definition this is a 90-degree angle. So if that's a dot, then that must be phi. Then looking through here, we've got vertically opposite angles. So when you have an X shape, when you have two lines crossed, then this angle will be the same on both sides. And then getting up into here, depending on if you want to use this triangle or this triangle, we have that Z shape. And so those two angles there are equal. So that's how we move from getting this angle starting here to here to here and to here. There are certainly other ways of doing it, probably 3, that all essentially work on the same principles. For example, this creates a Z. So I could have had angle phi here. And then I can go and work it into the other triangles in a similar fashion to this. Okay, so back to the question. Step 1 suggests consider the vertical direction. We are not sinking into the surface and we are not accelerating into the air. So what that tells us is that the sum of the forces up is equal to the sum of all the forces down. Now this question is based on the fact we don't need any friction. So if we're designed to go at 50 kilometers per hour, that means we don't require friction to do it. So this is a somewhat subtle way of saying at the perfect speed or the ideal speed. So this would be case 2 from the previous page. So going up, what is the force up? Well, the force up is Fn cos phi. That's the one bit there, and that's equal and opposite to the force of gravity. So we've got Fn cos angle phi equals Fg. And I'm simply going to isolate Fn so that later on I can substitute that into the next part of the formula. So Fn isolated is going to be the force of gravity divided by cos phi. Now, in many cases, you'd be getting a numerical answer here and then carrying it on and then continuing with the rest of the problem. So forces up equal forces down. Now, horizontally, and a reminder, there's no friction in this case, we have only one force. And this is the horizontal piece of the normal force. Here it's called FNH. It's opposite to our given angle. Fn is a hypotenuse, so this is going to be a sine component. Now, Fnet, by definition in these problems, is the centripetal force. In some cases, Fnet is a combination of forces if things are in the same direction or a different direction. In this case, Fnet is the piece of the real force, the normal force, it's the horizontal piece of it. So Fnet can be replaced with Fn sine phi. And Fc, in this case, we can replace that with one of our centripetal force formulas, and because we have a radius and a velocity, we'll be able to substitute mv squared over r. Okay, so now what we're going to do down here is we're going to take this formula that we've created here and we're going to replace Fn with what Fn is worth from the vertical part of the question. So it's just a straight substitution. So Fn is going to be replaced with Fg over cos phi. So this becomes Fg over cos phi. We still have the sine phi. And this is mv squared over r. Now, you've seen this a few times before in the course. What is sine over cos worth? And of course, the sine over the cos of the same angle can be replaced with tangent. So this becomes Fg tan phi is mv squared over r. And Fg, of course, is simply mg. So I'm actually going to running out of space. So I've got enough space. So this becomes mg tan phi equals mv squared over r. Here we see the masses are not important for these questions. So it wouldn't matter what size vehicle you put around here, we'd get the same result. And finally, as soon as we divide both sides by our gravitational field strength constant, which is worth 9.8, we wind up with a formula that says tan of angle phi is v squared over gr. And there we go. Again, a reminder, this is far more complicated than if you were to find a numerical value at the end of each step and then apply it in and continue on. So this formula here, you're going to wind up using without even knowing it. Here, let's actually use the formula to finish off this problem. So we're going to convert 50 kilometers per hour to the MKS units of meters per second. And we've got 1,000 meters per every kilometer. That leaves us with the units of meters per hour. And of course, we want to replace hours with seconds. So we know we have 1 hour is worth 3,600 seconds. Of course, 60 times 60 minutes and seconds gives us this value. And we wind up with 50 times 1,000 divided by 3,600 gives us 13.9 meters per second. We can now substitute this as our velocity. Of course, g is 9.8, and our radius is 50 meters for this curve. So, tan phi equals v squared over gr, which equals 13.9 squared over 9.8 times 50. And this gives us, after we take the arctan, we wind up with the angle of 21 degrees. So as you practice this, again, don't panic. This is more involved than you would do on a test. You would typically, again, find a numerical answer at the end of each section and then carry on. Our next example, in this case, this shows us the type of question you should be able to answer given the diagram for, in this case, case 1, but again, it could also be for case 3. So these are very, very complicated situations. So the diagram's given. Here's angle phi. We need to transfer this angle up into all the other triangles. So I just continue this line out to here. There's my 90, and I could call this angle dot. We already know that phi plus dot is worth 90 because 90 plus 90 is one angle in this triangle. So that gives me angle phi right here. And I can see that's a vertically opposite angle right there. So there's angle phi. And inside the force of friction triangle, we have this Z shape. So angle phi winds up right there. You can see that this diagram should be at least twice as big if you were drawing this on a test. But as it's done for us, hopefully you're able to sneak in the angles and read all of this. Okay, so in this case, we have case 1. We are traveling too fast in this case. So the road is designed to go at the ideal speed. We're going to exceed that. We're going to need a very, very large centripetal force, and that's going to come from two forces added together. And those are the horizontal force of friction added to the horizontal component of the normal force. Again, going very, very fast around a corner requires a larger centripetal force, so it's an addition. Okay, so our force is up has to equal all of the forces down, and our one and only force going up is this one right here, FNV. It's adjacent to the angle, Fn is our hypotenuse. So Fnv, our one and only up, is going to get replaced with Fn cos phi. Now we have two downwards forces. We've got FFV, that's the vertical component of the force of friction. We can see it's an opposite side to angle phi, FF being the hypotenuse. So this is going to be a sine component. So this is going to be FF sine phi. And what else have we got going down? Well, we've got FG. And we're going to replace that with mg once we get to it. All right, so here we go. So our one and only upwards force, the vertical component of the normal force, is equal to the addition of FFV and FG. FFV we already saw is the sine component, so that's FF sine phi, and FG is mg. So we are almost done. We're just going to clean this up a little bit. We simply want to isolate Fn and simplify this side as much as possible. We're really only one step away and a little bit of cleanup. So I'm going to divide both sides by cos phi. Fn is now isolated, and this will be FF sine phi over cos phi. We've seen that many times. And this is mg over cos phi. Now there's absolutely nothing wrong with stopping here, but we can clean this up a little bit. And most of you have done this unit in Math 12. So what would arguably be the simplest version of this formula would be FF tan phi plus mg, and the reciprocal of the cosine is the secant. This wouldn't be necessary. It's really not much simpler. Many people would just stop and leave this as mg cos phi. So there we go. That's taking a completed diagram, making sure we're able to get the angles put into all the associated triangles, and that we're aware that we have balance in the vertical direction, and we have to have an imbalance in the horizontal direction. In this case, two horizontal pieces of real forces are both directed towards the center, so we add them. So for the first question, I'm going to walk you guys through the diagram. Please, after you've done it, cover it up again and try and walk through it yourself without being guided. If you can't make these diagrams for cases like this, so case 2, ideal speed where no friction's involved, you really will struggle with these questions when we finally get to testing. So I'm going to hit pause, going to get slightly ahead with the diagram, and then walk you through it. Remember, sharp pencil, rulers, and large as possible so that you can fit into the space. Okay, so a little bit of background on drawing these. Start with easy things. Start with the ground. Get yourself something on the page. Then draw in your slope. In this case, we're banked at 35 degrees. Fairly far up this triangle I've created, I draw my bicycle as a dot. I shrink the entire mass down as if it was a lead ball. I've got two obvious forces. We already know this is a perfect speed question. There's no friction, which means we have only two real forces. We're going to have Fg, which will be equal to mg, and we're going to have Fn. One other thing I did, I drew in a dashed line. Of course, if this is graph paper, that would be there for you. And that's just indicating another horizontal. This allows me to bring in my 35-degree angle and create some triangles up here. Now I can work with this triangle, or I can work with this triangle. It doesn't really matter. They both have pros and cons. Let's make sure we can get that 35-degree angle inside both of these, though. So here's one of our ways. We had 35 here, which meant this would also be 35. This is, of course, a 90. This here is 90, which means this is 35 plus some other unknown angle I'm going to call dot. Back in here, I've got 35 plus dot equals 90. And then if that is a known amount, and that means this up here must be 35 degrees. Again, you can work this out. 35 plus dot is 90, so that's going to be 55 degrees. And then the rest of them all fall in. At this point, I'm going to let you work through this on your own. This was a longer than usual video. It's a rather challenging topic. I hope it goes well.